Okay, so there are a couple of issues that we have to discuss before formulating statistical mechanics from a purely quantum mechanical perspective. One is, as I mentioned at the end of the last lecture, okay, in our discussion in our classical statistics, if you remember, our system just moves from one microstate to the other microstate, just travels over all the microstates. But if you consider, for example, an energy eigenstate, and that is what we do in the microcanonical ensemble, we say that, okay, the system has a definite energy. Well, a definite energy state doesn't evolve in time. Whatever it is, it doesn't thermalize, it doesn't change at all. But of course, then the question is, can we really create a state of definite energy and isolate it from the environment? Well, that never happens in practice. All the systems you can think of are interacting with other systems. At the least, you have blackbody radiation. You are at finite temperature, you have blackbody radiation, so all systems will interact with all other systems. Furthermore, when you go to the thermodynamic limit, the differences between energy levels will be so small that even a very small influence will cause your system to move to different microstates, having almost the same energy but different. So this is not actually an issue. The more difficult issue, let's say, is if everything is interacting with something else. If you look at canonical ensemble or the grand canonical ensemble, even the definition of the ensemble itself takes into account interactions with the environment. But how do you talk about the quantum mechanics of a particle that is interacting with the environment? Let's say that as a simple case, let's just look at a spin system. Let's say that we have two spin 1/2 particles, spin up, spin down, plus spin down, spin up. And just for the sake of argument, let's say that as our system, we just take the first spin. Now, what is the wave function of that first spin? It doesn't have a wave function. We cannot talk about the wave function of the first spin only. We can only talk about the wave function of the combined system. Wave functions doesn't give us a suitable tool to discuss systems interacting with other systems. So we have to first come up with a formulation of quantum mechanics which we can use to study just a given system which might be interacting with the environment. That is where the density matrix comes into the game. Now let's look at quantum mechanics. Just we have a single particle isolated without interacting with anything else. This will be the wave function of my particle. And I can choose a basis and I can write this wave function. Let me also add the time dependence. I can write this wave function as some time dependent coefficients multiplied with the eigenvalues of some operator. Well, usually what we do is we choose the eigenvalues of the Hamiltonian. So these psi n's are energy eigenstates. So we know what the time dependence is. There are certain coefficients multiplied by e to power minus I e n of t over h bar psi n of x. And at the end of the day, we won't be measuring the wave function itself, but we will be basically measuring various expectation values. So what we will be actually interested in is expectation values of some operator, which will be d cubed x if we are in 3 dimensions, psi star xt, or psi xt. Now, for the time being, let's just look at, well, this will be time dependent We will study the time dependence later on, but let me keep the time dependence over. Well, I know this expansion. Let me just substitute that expansion. I will have two sums n and m. Then I will have a n star a m e to the power I over h bar e n minus e m of t d cubed x o n m psi n star x o psi m x, and this is what I call O n m. So O, the expectation value for this state, is given in this form. You see, this form is valid whatever the psi n's are. If they are eigenstates of the Hamiltonian, then a n star t a m of t has this form. If it has some other, if psi n's are eigenstates of some other operator, then they won't have such a simple time dependence, but still we can always write it in this form. So what is nice about this form is that psi doesn't appear over there. What we have is these coefficients a's. So we define a matrix rho, a function of t, the matrix elements is a m of t, a n star of t. Now, if we have O, this will be sum over n and m, rho m n of t, O and m. But you see, this is nothing but matrix product. If you sum over n, that is sum over m rho times O mm, which is nothing but trace of rho of t O. So if for any state, if I know rho, I know the expectation value of any operator. I don't need to know the wave function. If I know rho, I know everything that I can measure. I know all the expectation values. Well, let me use a slightly different notation. There's nothing wrong with this derivation. If you are used to wave functions, well, this is the correct derivation. If you are more used to the bracket notation, there is a simpler derivation of this result, simpler definition of this rho. Let's say that the expectation value of rho, this is the quantum mechanical expectation, by the way, is psi O psi. Let me just introduce identity in terms of some complete set. The easiest way to determine a complete set will be just take eigenvalues of any Hermitian operator. It can be the eigenstates of the Hamiltonian or some other operator. Well, then this becomes sum over n psi n O psi. This is sum over n n O psi psi n. I just changed the order of these terms. Sum over n n. Let me look at this object. That's an operator. You give it a state, it gives you a different state. That's the definition of an operator. And you are taking the diagonal elements of that operator and summing over all the diagonal elements. This is nothing but trace of O psi psi. Rho is simply psi psi. And if we go back to our earlier definition, you see this was the definition of rho. Well, let me just look at the Mn element. This is n psi psi m. This is just a n a m star, which is nothing but our earlier definition. So these two definitions are basically identical. Now, up to here, there is no advantage in using the density matrix. Yes, if you know the wave function, you know the density matrix. If the system has a wave function, then you know the density matrix. Just calculate this thing. And we can talk about the trace of rho. This will be the trace of psi psi. This is just 1. This is nothing but the total probability is equal to 1. Rho squared is psi psi squared psi, or this is just 1. So rho squared is just rho. As a special case, trace of rho squared is equal to trace of rho, which is equal to 1. Again. These are so-called pure states. Let's say that somehow you determine the density matrix of your system, or somebody told you what the density matrix is. This trace has to be 1. And furthermore, if you take the square of it and take the trace, if it is also 1, then it is what we call a pure state. That system has a single wave function, a well-defined wave function. Now, the advantage of this density function formalism is if you have systems interacting with an environment, if you don't know the wave function, or if, let's say, Pn is the probability that your system has the wave function. Let's say phi n. Okay, sorry for the notation. These phi n's are not necessarily the eigenstates of anything. You are given a system of many particles, let's say, with given probabilities. These are not the amplitudes, these are the classical probabilities. With given probabilities, your system will be in some particular state. Now, for these systems, rho is defined as Pn phi n phi n, sum over all n. Now, what is the trace of rho? Well, this is n Pn trace of phi n, but this trace is just 1. So this is sum over n Pn, which is 1. Now, what is rho squared? Well, now I have two sums. Well, in general, these phi n's need not be even orthogonal to each other. But just for simplicity, let's say, let me assume that phi n's are orthogonal. In that case, this is just mn, pn, pm, phi n, phi m, Kronecker delta and m. But this is sum over n, pn squared, phi n, phi n. If I take the trace of rho squared, this will be sum over n, pn squared, trace of, sorry, well, this trace is 1, pn squared. Now, pn's are probabilities, they are between 0 and 1. So their squares are always less than or equal to Pn. And equal, but this sum is 1. So for such states, trace of rho squared is less than or equal to 1. Now, equality holds if Pn are equal to 0 or 1. If Pn squared is equal to Pn only if Pn is equal to 0 or 1. But that means at most one of the Pn's can be 1, all the others should be 0 if the equality holds. But that means your system is created in a single wave function. Remember the definition of Pn. Pn is the probability that your system has the wave function phi n. Now here I made an assumption.
Hocam, was there a reason we said that this is a pure system?
Now this is called if trace of rho squared is less than 1, strictly less than 1, this is a mixed system. If trace of rho squared is equal to 1, this is a pure system. Now, okay, first here I made an assumption. It seems as if this is not the most general result, but it actually is the most general result. You see, rho is, as if I define it in this form. Look at rho dagger. Rho dagger would be, well, Pn star. Pn is a probability, it's a real number. Dagger of this one is just switch the order, convert the browse to cats, etc. But that is phi n, which is rho. So rho is Hermitian. If rho is Hermitian, I can always diagonalize it. Let's say if this condition is not satisfied, it might be that it is not satisfied. Just diagonalize it. It's a Hermitian. The eigenvalues, eigenstates will be orthogonal. I can also normalize them. So if that condition is not satisfied, diagonalize rho first. You get orthonormal basis, and just repeat the same argument. At least the final result that trace of rho squared will be the sum of some probabilities squared will still hold. Let's see, let's assume that I can ask, okay, what can you ask if you have a wave function? What are the things you can answer? What's the probability that it will be in a given state? That is something we can ask. Let's say that what is the probability that our system will have energy En? And if I know the density of states, I can answer that question also. Let's calculate this one. Psi n rho psi n. I'm just looking at the diagonal element. Let's say that psi n, if psi n is some energy eigenstate, what is the probability that my system will be in this energy eigenstate? Well, this will be equal to Pn psi n, well, let me say Pm, phi m psi n, sum over m Pm psi n phi m squared. Now you see, what is this? This is the probability that the state phi m is observed in the state psi n. That's that probability. Multiply by the probability that my system is in the mth state and summed over all m. Well, that is exactly the probability that the given system is in the n psi n state. By the way, you can also write the same matrix element as trace of rho psi n psi n. So I can talk about, if I know the density matrix, I can talk about the probabilities that my system will be in this state or that state. So whatever you can answer using wave functions, you can answer using the density of states. And for example, I cannot write down a wave function for such a system. The system doesn't have a wave function. But I can use the density of states. So if I'm given such a system, I cannot use a wave function or solve the Schrödinger equation for that system. I don't know the initial condition, I don't know the state, but I can still write down the density of states for such a system. And once I know the density of states, I can answer all the other any question that you can ask me. If there is a wave function of the system, if I know the wave function that it's definitely in one wave function, well, then I know that I can write the density of states and still study the same system using the density of states. So in that sense, density of states is more general than the wave function. Well, how will this come into the statistical description? Well, what do we do in statistical physics? We have our, this is my system. Let me call that A. And I have the environment. Well, let's say that all this and my system plus the environment B has a density of states, let's say rho AB. It will depend on all the quantum numbers corresponding to my system, my environment, or the combined system. I will be eventually calculating the expectation values of operators of my system my particular system A. This is what I'm interested in. This will be the trace of OA times rho AB. You see, AB can be a pure system also. My whole universe, you can say that, okay, the whole universe has a wave function. A is my system, B is whatever remains in my universe. And I don't know the wave function of the universe, so it won't be so much useful, but still I can talk about it. So this is what I would like to calculate. If the universe has a single wave function, fine, I can still talk about its density of state, density matrix. Now, what does that trace stand for? Well, it's a trace over the degrees of freedom of A and B, all those degrees of freedom. We will make an explicit example of this. So if it is too abstract for the time being, it will be more concrete in a moment. Well, this I can write as trace over the degrees of freedom of A times trace over the degrees of freedom of B, or A rho AB, which will be trace over the degrees of freedom of A. Well, this doesn't depend on the degrees of freedom of B, so I can just take it out. Trace of the degrees of freedom of the B, rho AB. This thing is what I call rho A, the density matrix for the A system only. It doesn't depend on the properties of the B system. So rho A for such a combined system is just take the density matrix of the combined system. You see, the whole system can have a wave function. Even if the whole system has a wave function, the system I'm interested in, system A, will not have a wave function. But still, I can calculate the density matrix of my system if I know the wave function of the whole system, by taking the trace over the degrees of freedom of the B system. Okay, this was maybe a bit too abstract. Let's go to our two-spin systems. Let's say that my system is this. I have a two-spin system. This is my spin A, this is my spin B. Spin A doesn't have a wave function. Well, on one hand, I can write straight away what the density matrix of my system is. Well, what is the probability that my system A will have a spin up? Well, 1 over 2. What is the probability that it will have a wave function of spin down? It's again 1 over 2. This should be the density matrix. Now, when I make an observation of my system only, without knowing what the B system is, I know that I will only measure the wave functions spin up or spin down. I won't be measuring the spin up plus spin down wave function of my system A. How can we drive this? Let us start with what is rho AB? Well, rho AB is this one, 1 over 2, up, down, minus down, up, times up, down, minus down, up. This is rho AB. Now let me just open it up. Up, down, minus up, down, down, up, minus, down, up, down, plus, down, up, down, up. Well, what is rho A? Rho A should be trace over the degrees of freedom of B of rho AB. Well, the B system can be either in spin up or spin down. The trace will be spin up for the B system, rho AB, spin up for the B system, plus spin down for the B system, rho AB, spin down for the B system. You see, I don't have to use the same basis. For example, I could have chosen to use the basis of spin up in the x direction, spin down in the x direction. In that case, I will get many terms, but the trace is independent of which basis you use. So the simplest one would be just stick with the spin up in the in the z direction and spin down in the z direction. Well, what is this? Well, let me look at this one first. Remember, the first spin is A, the second one is B. I need to have the overlap with spin up B. You see, this term over here, or this term has spin down B. So this product doesn't receive a contribution from this one. And this also has, this term also has B spin down. So multiplying from the left with B spin up, it will give me 0. I will get contributions from this one and from this one if I multiply by spin up from the left. But keep in mind that I'm also multiplying by spin up on the right. And only this term, this product, has spin up for B on the left and spin up for B on the right. So this will be, that term is the only contribution, 1 over 2 spin up for the B spin, spin down, spin up, spin down, spin up. Well, similarly, the only contribution to this one should have spin down for B, both in the bra and also in the cat. And that is this one only. So I will get, so this is spin up for the B spin, plus 1 over 2 spin down for B, spin up, spin down, spin up, spin down for B. Well, B, and also let me just specify this, what I mean by this. For example, this is AB, is spin down for A times spin up for B. This is the notation, the product of the wave functions. So this just gives me 1 over 2 spin down, plus 1 over 2 spin up, spin up. This is my rho A. As I expect. Well, this was kind of trivial in the sense that already, if you look at this wave function, I don't know, I'm not making any measurement of the environment. Whatever the state of the environment is, my system will either be spin up with probability 1/2 or spin down with probability 1/2. So let's do another example.
Hocam, before that, I would like to ask, in terms of matrix representation, it may be a little bit crowded, but what does it mean summing over B? I mean, the trace part is normally is the sum over the diagonal terms, but in this case we are summing over B. What does it mean in terms of matrix?
I don't really know how to show that. That's why I prefer to stick with this bracket notation. It's easier over here. Because you see, this row A, if I want to show this in matrix notation, row A is 1 over 2, 0, 0, 1 over 2. Row AB is, let's say, 1 over 2. No, let's say spin up, spin up, spin up, spin down, spin down, spin up, spin down, spin down. Now these are all zeros. These are all zeros. No. These are 1 over 2, 1 over 2, minus 1 over 2, minus 1 over 2. This is my row AB matrix. How would I show the trace over this 4 by 4 matrix so that I get just a 2 by 2 matrix? I'm not so sure. So that's why I prefer this method. It's more clear to me. Anyway, it will probably be easier to show it if we show row AB not as a 4 by 4 matrix, but as the 4 sides of a 2 by 2 cube. That I'm sure there is a way to get that from that 4 by 4 matrix to the 2 by 2 matrix, but it will probably be more complicated than this one. Okay, okay, this was kind of a trivial state to start with. Can you suggest some other, maybe more complicated state rather than this one? Okay, first of all, the B system will be definitely either up or down. I mean, up or down is a basis for the B system, right? So I can write any wave function of the combined system as a superposition of up for B or down for B. This is for B. What are the coefficients? Well, I don't know. And with certain coefficients A and B. Well, this is the most general wave function you can write for this two-spin system. Psi A and psi B is some arbitrary wave function of the A system, not necessarily spin up or spin down. Well, we can do the same trick. Rho AB will be psi AB, which will be A psi A spin up psi B plus B psi B spin down psi B times A star psi A up plus B star psi B down. Well, taking trace over the B degrees of freedom is just summing psi A B. B is up. B is up. You say, what will this be? This will be psi AB, psi AB spin up for the B system. But if you look at this expression, if B is spin up, only this term will contribute. So it will be just A squared psi A, psi A. Well, this is nothing but the probability that the A system, the A system will be in the psi A state. A squared is just that probability. Let's see, B system can be psi down. Well, similarly, this will be just B squared psi B, psi B. So I know my density matrix now is just the sum of those two. Well, what is the probability that my A system will be spin up? Well, probability of spin up A is nothing but spin up rho A spin up. That's what we had seen before. Here. This will be, sorry, A squared spin up psi A absolute squared plus B squared psi B absolute squared. The probability that my system will be spin up is the probability that my system will be in A times the probability that system A has spin up. The wave function A will be measured as spin up plus the probability that my system will be in state psi B times the probability that if I make a measurement of psi B that it will be up. Now also pay attention that we have two different probabilities here, two different averaging. One is the quantum mechanical averages, quantum mechanical probabilities. So this is psi A. This is what I mean by quantum mechanical probability. You see, my system need not be spin up. If my system is in the state psi A, if I make a measurement of its z component of the spin, there is a probability that it will be spin up, there is a probability that it will be spin down. It doesn't have a definite spin before the measurement. Once I measure it, it will be either spin up or spin down. And this is the probability that I will measure it to be spin up. And then there is the other probabilities, A squared, for if I consider my system A only. This is the so-called classical probability. Now we can also think of it in this way. Let's say that I have given you n particles. I don't know their quantum mechanical wave function, but I know that with given probability, each particle will have this wave function or that wave function. So this density matrix, in a sense, describes such a system also. So what we had achieved in the second hour. First of all, I don't have to work with wave functions. There is this density matrix formalism, which is in fact more general than the wave function formalism. Because if I have a wave function, then I can always define, if I know the wave function, if the system has a definite wave function, I can always talk about the density matrix of the system. If my system doesn't have a wave function, let's say if it is interacting with an environment, it is so-called entangled with other degrees of freedom in the environment, not in my system, then I cannot talk about the wave function of the system. You see, if you look at this one, the wave function of system A is neither psi A nor psi B. None of them is a wave function of my system. The wave function of my system is neither A psi A plus B psi B. You see, the wave function for example, this wave function also has the probability that the wave I will observe the system in state A is A squared and state B is B squared. If you just look at the probabilities, it seems as if this function has the same property as the density matrix of this row A, but it does not. They are different, they describe different systems. And although for this system I cannot write down a wave function, I can still write down a density matrix. I can study its evolution. How the system will change, I can answer any question that the wave function could answer using density matrix. So in this sense, density matrix is more general in this, and I can use that to study even systems interacting with an environment with a heat bath. And that was what I was hoping to achieve. You see, in our statistical description, we should be able to describe systems interacting with environment, so-called heat bath. Now I have a formalism in terms of this row, which allows me to describe my system in terms of the systems that are interacting with the environment. Well, the next steps we will take will be similar to what we had done with the density matrix in phase space. You see, we had a density in phase space of the ensemble. And when we wanted to calculate the expectation value of anything, we actually multiply it with the density and integrate it over all the degrees of freedom. So it will be, in fact, analogous to So the next thing we will do is look for what are the possible density matrices for systems in equilibrium with the environment. The first thing we will do is how does rho change in time? And we will derive the analog of Liouville theorem, so which will tell us that rho is also a conserved operator. Its formation furthermore, in equilibrium it will be conserved. So it should be a function of energy, etc. And in fact, at the end of probably next hour, what we will have shown is, well, we can actually do what we had done before using the quantum mechanical states. We are justified to do that. And then, of course, we have the problem of identical particles. It's the wave functions of identical particles have certain properties, certain symmetry properties. We should see how we can implement those. So any questions before you go and before I run out of my chart? So I would advise you to go over at least the Liouville theorem. It's that density we discussed over there. We said there we also define the density we normalize it to 1. Here rho is also normalized to 1. Because, as I said, we will be basically repeating the same derivation for the density matrix.